Okay, so when we embark on these free response questions, what I'm going to do is this. I'm going to go at the free response question without looking at the what they call the scoring guide first. I'm going to take it on as if I was going to answer the question. So there'll likely be places where I miss points, almost certainly. Hopefully no places where I make egregious errors or wrong physics, but I might not realize they were expecting a point for this or that. To me, if I just go through with the points and show you it's just going to be too sterile. So I will want you to see the thought processes involved. I will also try to give you, maybe here at the start, just an outline of some things that you might want to consider. Maybe at that point you pause it and give it a shot. It's up to you. So here's my thought on this. One of the things about momentum questions is you've gotten far enough in the course that they almost always can sneak in energy somewhere. So like, for example, this first part of this question is energy. It starts at rest at a certain height, and they give you the velocity at the bottom. It's an expression, but they give you the velocity. So you can figure out kinetic energy. Therefore, if this is a frictionless ramp, that means this would be the potential energy here. Whatever the kinetic energy is here just before the collision, you could find the height that way, if that's what they're looking for. So let's see let's read it and make sure. Small block of mass m, released from rest at the top of a curved frictionless ramp. Okay, so that means that all of the potential energy it has here is going to be kinetic energy just before this collision. And they give us the velocity, and they give us the mass, so we can find that kinetic energy, which means we have an expression for the potential energy as well. Then it hits the bigger one, and momentum comes into play. The larger block, they give us a larger block speed. They don't say that the two stick together, so I'm assuming they don't. But they do give us the speed after the collision for the larger block. I'm down here somewhere. Yep, they're going to want the speed of the smaller block, it looks like. We'll come to that. Especially answers the following questions in terms of the given quantities. So the TVO, the 1/2, like anything that they've written down so far is perfectly fine. And of course, G and that kind of thing. It qualifies as a fundamental constant. So determine the height h of the ramp. Okay. So this paper's a little small. We're going to have to hopefully have a copy of this in front of you. So what we know is there was just potential energy at the top because it started at rest. And that potential energy would have been the mass of the block, G times, and they call it H, so literally mgh. That is the mechanical energy initial, and it is the potential energy. When it gets to the bottom, all of that, because we're assuming H, this is 0, all of that energy is now, mechanical energy here at the bottom we'll say, in the form of kinetic energy. This is just before it hits the other block. So it still has a mass of m. They give us the velocity at the bottom of 3.5 times VO, whatever VO is. So we actually have enough to set these equal to each other. Once again, you're not worried about the fact that you don't have a lot of numbers, and I don't want you to use numbers, but we have an expression for this, and all this stuff that we have here is stuff they've given us. H they gave us, so we're all legal. So we set these two equal to each other. Conservation of energy. So mgh equals 1/2 m this squared. 3.5 VO, the whole thing squared. And we're solving for h. The m's do cancel. So divide by g. Now here's the thing. You're going to end up with, one way of looking at this, is 3.5 VO, the whole thing squared, over 2g. You have h, this brings me to an important point. You have h by itself. You have fulfilled what they asked you to do, which was determine the height of the ramp from which the thing was released, and the only things you're allowed to use are stuff they gave you or fundamental constants. We did that. Have we simplified it? Could we square this? Sure. what benefit do we have? What benefit do we have? We've done what they asked. This is not an algebra exam. This is not a, can you reduce stuff? Can you square things? I would say leave, once H is by itself, leave what you got. If it turns out that you need a simpler version of it, or they say they want you to show as a specific thing, go ahead. But I would just leave it for now. Once H is by itself, I'm done. This is part A, finished, complete A, done. Because I'm gonna end up forgetting, just, I'll square one of these wrong, or and then you're gonna be like, you might lose points. They can't tell you this is wrong, and there's no thing here, no note in here that says answers must be simplified. They won't do that to you because they're rightfully so. They're only interested in physics. All right, so I have this value for the height. A is done. B says determine the speed of the small block after the collision. Okay, so really, the height does not really carry over, I don't think. Maybe I'll be wrong, and I'll find out I'm wrong in a minute, but I don't think the height carries over. So what we're now looking at is we have this block M that is moving at 3.5 VO to the right and is colliding with another block that is 1.5 M. Yes. They have, so the momentum before is this, and then after the collision, all we know is that the larger block, so let's see, this is the before, or initial, and underneath it we'll show the after. Afterwards, I know that the 1.5 block, 1.5 M block, is moving to the right with a speed of 2 VO. That's all I know. I don't really know what this one's doing. Is it moving this way with a speed? Is it rebounded backwards? I really don't know. But it is going to have something, I think. I don't think it'll be stopped. Usually it only stops if the objects are the same mass. So we need to find the final velocity of this block. Okay. This is our after situation. And what we know is that momentum is always conserved. That the momentum before, initially, has to equal the momentum final. And I always write them spread apart like this. Because initially, in some problems, there could be more than one object. In some case, sometimes there's only one. In problems like this one, there's actually two objects later on. So I like to leave plenty of space. And then I just look at my situation. Before, this block was at rest. The only thing that had momentum was the little guy. So its momentum would have been 1m times 3.5 times VO. That has to equal the momentum afterwards, which has two objects. I know one of them, I'm going to put it over here, is a positive, because we're assuming right is positive at this point, since I made this positive, like that. So positive 1.5 M moving at 2 VO. The little guy, all I know is it got an M. I don't know how fast it's going. That's what I got to find. So it all comes from the conservation of momentum. Okay, so I have 3.5 MVO on the left. Over here I got MV final. And here I got plus 3 MVO. Oh, wait a second. M's cancel out. They don't have the same mass, but they're relative. They describe this one's mass in terms of that, so that M gets to divide out. So I got 3.5 VO equals V final plus 3 VO. So I'm going to subtract 3 VO from both sides, and I have 0.5 VO. So this block, and it's positive, so this block after the collision is moving to the right with a velocity of 0.5 VO. So it all comes from the conservation of momentum. Collisions are all about conservation of momentum. Next, it says the larger block slides a distance d before coming to rest. Determine the value of the coefficient of kinetic friction mu between the larger block and the surface on which it slides. Okay, so then they switch gears completely. Momentum is now gone, and you are squarely in the realm of forces and energy. In fact, energy then forces. Here's how we're going to attack this one. So, I don't care where it came from. We now have an object whose mass is 1.5 m, moving at 2 VO, whatever that is, for a velocity, and it slides to a stop. 1.5 m. Its final velocity is 0. Okay. Ooh, it slides a distance d. So since they give us that distance, we're allowed to use it. Oh, now come on now. We've done energy recently enough. Alarm bells are going off in your head, right? Okay. What kind of energy did it have here? It was moving. It had kinetic energy. And that kinetic energy changed. It went away, didn't it? So there was a change in kinetic energy. Now, if you remember anything from energy, you know that a change in kinetic energy is equal to the net work done. But you also know that work is force times distance, which they allow us to use now. But you're like, they're not letting us use force. Chill. Alright? Chill. Let's see what happens. Let's go with what we know. So, first of all, change in kinetic energy. It had this kinetic energy at the beginning. We can calculate it. It has nothing at the end. So, the change is actually negative because it used to be your final, which is 0. So change in kinetic energy is your final, which is 0, minus 1/2 times 1.5 m, that's the mass, times 2 VO, the whole thing squared. That's your change in kinetic energy. So your change in kinetic energy comes out to be, let's see, that's going to be a 4, that's going to be a 2, that's going to be, if I do it right, it's a 3m VO squared. Square the 2, that's 4, but this we're going to divide into it, make it a 2, and then 2 times 1.5 is 3. Yeah, I think I got that right. Now that is equal to the work done. So that is equal to the net force times that distance. Well, what's the net force? What's the only force that it's acting on this thing to cause it to slow down? That's right. It's friction. It's friction. Now we have to go to the equation that nobody remembers. No matter how much I teach it every year, nobody remembers it. Like, did we learn that? The force of friction is mu times the normal force times distance. That's why mu is, they asked us for mu, because there it is. Now, normal force. N is not one of the things they gave us. But the situation is laid out. That's a horizontal surface, right? So the weight of this, 1.5 m times g, is the same as the normal force. So we actually know the normal force. So I have 3 m VO squared, that's your change in kinetic energy. I dropped the negative because I'm going with magnitudes for now. What would happen is this force is negative, and that's so they would go away anyway. Equals mu times the normal force, which is the same as the weight. So that's going to be 1.5 mg, and then the distance comes in because we're doing work over here. All right. M's go away again. Isn't life grand? And I'm after mu. So I'm going to do 3 VO squared divided by 1.5, don't forget G, and don't forget capital D, equals mu. Once again, just stop right there. Now, you could simplify it. 1.5 goes into that twice, okay, fine. But you don't have to. Like, if they give you a point for the correct answer, and you make a mistake when you divide and you make that a 3 or you do something like that, and they don't give you that point, that's a tragedy, because they'd probably give you the point for this, because their job isn't to check to see if it's simplified. So just be careful about being too, it could be not only a waste of time, if you make a mistake, it could kill a point. We'll look and see what points come with this one. So this would be, just to clean it up, 2VO squared over dg would be mu. To recap, I looked at it, I see a change in kinetic energy. I immediately think, work done. I know when they say mu, it's force. It's involved in the frictional force. So, and there's force in work, right? And they give me distance, which is another clue that work's got to be involved. So I find that change in kinetic energy. I set it equal to the work, the force times the distance. Next trick, I got to look at it long enough to realize, oh wait, the normal force is just the same as the weight. I'm not allowed to use N for normal force, but I'm allowed to use G and M and 1.5. So I get down to this. Now let's see. And the last one on this says, indicate whether the collision between the two blocks is elastic or inelastic. Justify your answer. I would say elastic. I got a couple options here. I would say elastic because it doesn't just stick together. But there is one other possibility. See, we'll have to look at it and see what they say. Collisions can run from perfectly elastic, where they bounce off and there's no loss in kinetic energy, to perfectly inelastic, where they stick together. But most real collisions are somewhere in between. There's some sticking going on even when two steel balls hit. They stick for a little bit and they bounce off each other. And there's a little frictional loss there. So, and things, they may stick together for a while, but then it's come apart later. So the only way to verify if what they mean by this, if all they mean is do they bounce off or stick, I'm going to go with elastic. They bounce off because they're not connected. But if they mean, is it perfectly elastic? I'd have to see if the kinetic energy after the collision is the same as it is before. Now I'm going to go with, I'm taking this test, I have X amount of time, they bounced off, I'm just going to say the objects did not stick together, they bounced off each other, therefore it's an elastic collision. Let's see what that would do. So let's go look at the answers for this. Alright, part A. That would be over here. So 1 point is earned for any use of conservation of energy. So as soon as I wrote this, that the potential energy at the top, is clearly what that is equal to the kinetic energy at the bottom, I get that point. I don't necessarily have to say it. It's implicit in what I wrote right here. 1 point is earned for a correct expression for the initial potential energy. So not only do I get points for showing that the potential is equal to the kinetic at the end, I get a point for this being correct, mgh. 1 point is earned for a correct expression for the kinetic energy at the bottom of the ramp. I get a point for that. So conceivably, I could do something goofy, like forget the half in this, but if I was clear that this was kinetic energy and this is potential, I could get the point for setting them equal. One point is earned for the correct answer. Now they lift their correct answer. I don't know if you can see it. I'll zoom in here. (3.5 squared VO squared over 2G). So, yeah, they didn't even bother squaring the 3.5 either. This, they say, or equivalent. So ours would have been fine over here, if you can see it. Our answer here would have been fine. So, all right, so Wellborn gets all 4 points there, I think. The only thing that I might do is specifically say something like mechanical energy at the top equals the mechanical energy at the bottom, just for the conservation of energy piece, just to make sure they all know that I knew that. But I think I get all those points. All right, for the next one. I repeated that. Okay, part B. 1 point is earned for any use of the conservation of momentum. If you see that it's a collision, first of all, let me back out. So this is part B right here. This is part B. If you see that it's a collision, for the love of God, somewhere on the page, write initial momentum equals final. Show that you know the conservation of momentum applies. Because you do that, for any use of the conservation, that's a point. 1 point's earned for a correct expression for the initial momentum. So then, if you write this, then the next point is, do you have the right initial momentum? M 3.5, yep, okay. 1 point is earned for a correct expression for the final momentum. That would be MV, they just called the missing void V, so that'd be fine. And then this mess, so yep. So 1 point for this side being right, 1 point for this side being right. 1 point for the correct answer, which is 0.5. So only 1 point for this. You got 1, 2, 3, 4 points, one of them just for writing that, one for clearly describing what the momentum looked like in both cases, and then a point for the answer. Part C, the one with the coefficient of friction. Alright, so my answer is done, is what they call the alternative solution. That's me, I'm a rebel. So the alternate solution. So there's nothing wrong with an alternate solution, we just took a different approach. I took the energy approach. So 1 point is earned for any indication that, oh, I lost my page. Oh, good, right? Okay. 1 point for any indication that the work done on the block as it slides is equal to its initial kinetic energy, or change in, which is what I said, so yes. So the work done on the block, I said it right here, work done on the block equal to its initial change in initial kinetic energy. And you get 1 point for a correct expression for the work done. So I guess that would be here. They would give that here. So that when you get all the way down to mu, normal force being the weight, and D, and 1 point for the kinetic energy being correct, which I would have done up here. I'm just making sure I got it right. I think I did. Alright, and then 1 point for the correct answer, which is 2 VO. Yep, okay, so we're good. So now let's look at their other approach, the non-alternate one. 1 point is earned for a correct relationship between the friction and the acceleration of the block. Okay, so they went the forces F equal ma route. In fact, let's just try it real quick and see what that would look like. So let's say we didn't take the change in kinetic energy route. We just said we have a block of 1.5 m. It's got this velocity of 2 VO. Alright, and it's going to go to 0 velocity. Still the same mass, it does it over a distance. So instead of looking at work, I think they go kinematics. They would say, alright, my original position we'll call 0. My original velocity is 2 VO. My acceleration is going to be unknown currently. But if I find that, I'm going to be in good shape. That'll help me find the net force. Final position is D. Final velocity, 0. Comes to rest. Time it takes, I have no idea what time it takes. So this is the one that I don't care about. So that helps me choose the correct equation. That would be the third one. V final squared equals V initial squared. I guess I've been using O's. Plus 2G delta X. All right, I'm not 2g, 2 acceleration. This isn't a vertical problem, so whatever that acceleration is. And we have everything here except a. I think that's what we're going to go after. So v final is 0. V initial is 2 VO, so you're going to square that. So you're going to end up with 0 equals 4 VO squared. Over here, you're going to have plus 2AD. Change in position is D. And you're solving this for the acceleration. So I'm going to have negative 4 VO squared divided by 2D equals A. And the acceleration would be a negative 2 VO squared over D. Alright, I got the acceleration. Whoop-de-doo. But then there's Newton's second law. Net force is equal to mass times acceleration. Well, that net force is friction. So I can also write, the other way to look at it is the net force is equal to the force of friction. So I can set them equal. I can write the force of friction is equal to, the mass is 1.5 m times this mess, this acceleration down here, times negative 2 VO squared over D. But friction, the formula nobody remembers, is mu normal force. 1.5 m times negative 2 VO squared over D. Normal force, though, is just the weight of the object we talked about earlier, so that's mu times 1.5 m times g equals 1.5 m times negative 2 VO squared over D. Alright, so the 1.5 m's are going away. Mu is going to be, the negative is neither here nor there at this point, but 2 VO squared over dg, which is the exact same answer as the other one. Now, I want you to tell me, when we started energy, what did I tell you? I said, when you have a choice, energy is usually going to be your easier method. Now, if you don't know or can't remember, change in kinetic energy, but to me, this side, that's like kinematics and then forces. Here, change in kinetic energy. To me, this is a little simpler. Now, one or the other is going to come to you during the test. You just do whichever one works for you. You're going to get points for either one. In fact, for this method, you get a point earned for recognizing that the force of friction is equal to ma. A point is for picking the correct kinematic equation. A point for using the correct initial speed of the block to, in other words, calculating this acceleration. Then it just says substituting expression. It doesn't say you get a point for this. So it says 1 point is earned for using correct initial speed of the block. So I don't know if you have to do 1 point is all of this. In other words, coming up with this statement down here. And then 1 point for the correct answer. So roughly 1 point for F equals ma, 1 point for doing the kinematics, and 1 point for setting it all up, and 1 point for the answer. A little more vague on the points there. I like my alternate solution better, but of course I do. Because it's the better solution. It's a more elegant one. Alright. Part D. 3 points. Interesting. So 1 point for indicating the collision is inelastic. Interesting. So I would have, my quick answer, which was just to say it's elastic because they bounce off, would have been not right. I wouldn't have gotten that point. But remember when we went over that, if you rewind the video, I said if we really wanted to know, I'd have to see what the kinetic energy is before and after. And if they're not the same, then I have to say it's inelastic. 1 point is earned for indicating the reason it is inelastic is because the change in kinetic energy is not zero. There you go. So yeah, I wouldn't have gotten any points for my answer, even though it bounces off. So you would have had to have shown the initial kinetic energy. If you'd have just taken the initial kinetic energy when it was a single block, so final minus initial. So the final had the two blocks. One was moving at 0.5, if you recall. The other one, you take that final kinetic energy minus the initial, which was the kinetic energy of the block just as it got to the bottom of the ramp. When you subtracted them, there was a change. And if there's a change, that means it wasn't conserved, and so the collision it has to be classified as inelastic. Even though they bounced off a little, there was energy lost. It wasn't perfectly elastic. So there's the lesson learned. I suspected this. I'm not going to lie. I was a little lazy and didn't feel like doing that. If I had time on the test, I would definitely have done this. I knew to do this, but I got lazy. All right.